Hi everyone, and welcome to the first lesson for Chapter 6. We're doing derivatives of exponential and logarithmic functions. Now it's been a while since we did derivatives, so you probably don't remember all of the shortcuts and rules about doing it. So make sure you watch through all of the examples here because we're going to be going over the chain rule and the product rule and the power rule, just to kind of familiarize you with how everything works. So we're going to start off with talking about the derivative of an exponential function. For an exponential function, we have a constant raised to a variable. So a represents a number and the x is our variable. So when you do the derivative of a power function like this, it's going to equal the power function times the natural log of this base number, whatever that constant was. So let's do an example of that. In example 1, we need to find the derivative of the function. I have y equals 10 to the x squared. Now, this is an exponential function because I have a constant raised to a variable, but this isn't just a plain variable, it's a function itself. So that's how I know I need to use the chain rule, because it looks like this, but there, where the x should be, there's a function. So to use the chain rule, I'm going to let u equal x squared, and I'm going to rewrite my function as 10 to the u. Then I'll do the derivative of both of these. Here I'm going to use the power rule, so the derivative of u is going to be, I'll bring the 2 to the front and go down 1 on my power. Over here, I'm going to apply the formula that we had earlier. So I keep the 10 to the u, and then it's times the natural log of 10. Okay, so next what I'm going to do is I'm going to take my derivative of the inside function times this derivative of the outside function, 10 to the u natural log of 10. And then I'm going to replace the u with what it was. So the final answer of this is going to be 2x times 10 to the x squared times the natural log of 10. Now, there isn't really a best way to put this in an order. It just kind of looks a little messy. If you wanted to, you could do some parentheses here, so it kind of separates out the things that are multiplied together. But there really isn't a best way to write this. Okay, so let's look at logarithmic functions next. A logarithm is the inverse of an exponential function. Okay, so if I have like 2 to the third equals 8, then I would write log base 2 of 8 equals 3. It kind of like undoes the exponential function. It tells you what the variable was that was up here. Okay, so if we're given a logarithmic function, okay, what we have is we have a base number. That's a constant. This a is a constant, and this is our variable here. So it's log base a of x is going to equal 1 over this x number times the natural log of the base number. Okay, so let's do an example to show you how that would work. I have log base 10 of 2 plus sine x, and I need to find its derivative. Okay, so in this one, I notice there's still an inside function here. So I'm going to need to use the chain rule again. So I'm going to make u equal this inside function. Okay, and my outside function is going to be f of x equals log base 10 of u. Now I'll do the derivative of both of these functions. The derivative of this one is going to be, the 2 is going to disappear because the derivative of a constant is 0. The derivative of sine is cosine. Over here, the derivative is going to be, let's follow our formula. I have 1 over 10, x, or u in this case, u, times the natural log of 10. Now I'm going to multiply these together. So it's cosine x times this derivative. And finally, what I'm going to do is replace the u with what it was, the 2 plus sine x, and I'm actually going to multiply this. This is cosine x over 1. Okay, so multiply the numerators, multiply the denominators, and I'll replace the u with this u. So I get cosine x over 2 plus sine x times the natural log of 10. And that's my final answer there. That's the derivative of our function. Let's look at the natural exponential function next. E is a number. It's defined using a limit, actually. So we learned about E last year and how to actually calculate it, and we did it on our calculators. But it's the limit as x approaches infinity of 1 plus x to the 1 over x. This number shows up a lot in scientific applications, so you'll see it a lot when you go into the sciences. And that's why we have it programmed into our calculators in several places. But when you do the derivative of e to a variable, it's going to just equal e to that variable. So it's kind of useful when we do functions and finding the derivatives that it's kind of an easy derivative to find. So let's take a look at an example. I have y equals e to the tangent x. Now again, this variable that's supposed to be up here has a function in it. So I'm going to use the chain rule again. So I'm going to let u equals the tangent x and y equal e to the u power. Now I'll do my chain rule. Derivative of u is going to be secant squared x, because the derivative of tangent is secant squared. And the derivative of e to a power is just going to be e to that same power. Now I should multiply these together, so I get secant squared x e to the u power. And I have to replace that u with what it was at the beginning. So this is going to be secant squared x times e to the tangent x. And again, there's no easy way to write this. If you wanted to, you could put parentheses, and that would help show that this is multiplying, so you're not thinking you're doing the secant squared of x times this, so that this is not in the secant function. But other than that, there's not much you can do with it. Okay, let's look at another example for the natural exponential function. Here I have e to the negative 4x times sine 5x. So I not only have the chain rule going on with this power on my e, but I also have a product rule going on and an extra chain rule over here. So there's a lot going on in this function. Okay, so we're going to start out with defining u and v. So I'm going to start out looking at this e to the negative 4x. Okay, so if u is e to the negative 4x, then v is going to be this part here. Okay, and I'm going to find their derivatives. Now, when I find the derivatives, I'm going to use the chain rule here. So I'm going to make w equals negative 4x, and I'll leave u as e to the w power. When I do this derivative, this has a derivative of negative 4, so it's negative 4. The derivative of this is e to the w power, and the w is negative 4x. So that's the derivative of my u. Okay? For v, I'm going to let, let's go with y, equal, oops, we already used y. Let's do v then, or z. There we go. Z equals 5x. The derivative of sine is cosine of what z was, and the derivative of z is 5. So that's my v prime. Now for the product rule. Okay, it's the derivative of the first times the second. So this derivative times this v plus the derivative of the second times the first. So it's 5 cosine 5x times e to the negative 4x. Okay, so this is a bit messy. To clean it up, the book actually factors out that e to the negative 4x because it does show up in both of these things that are being added together. So the book cleans it up to make it look like this. E to the negative 4x times negative 4 sine of 5x plus 5 cosine of 5x. And that does clean it up a little bit. This was very messy, so it just combined it a little bit. And that's it for that example. In the next video, we're going to talk about our natural log function and finding its derivative. So make sure to watch that before moving on to your homework.